Um, Hi, hello everyone. Hi, this is Wei. I'm the registrar in metabolic medicine, and today I'm going to share a very brief talk on immunochemistry. So the focus for today will be first some recap of some immunology basic concepts, and the second will be a very brief introduction on different kinds of immunoassays. In terms of the immunology basic concepts, I believe you're very familiar with all of them. Just a very brief recap. So, what is antigen? Antigen is a molecule that can react with antibody, and we also have another term called immunogen. So, immunogen is a molecule that's able to induce immune response. So, basically, this table is trying to differentiate between the antigen and the immunogen. So the key information is that all the immunogens are antigens, but not all the antigens are immunogens. So there's a group of antigen that's not able to induce the immune response by itself. So this group of antigen is called hapten. So hapten is small molecules, small molecular antigens, such as some lipids or drugs or polysaccharides, that's not able to induce the immunological response by itself. So what we can do is to add an adjuvant to it. It's usually a large protein, and to make the hapten to be immunogenic. So it's able to induce the immune response. Another term, another concept is called epitope. So as we can see from the picture here, so this is the antigen. So this antigen has three different kinds of epitopes. So usually, one antigen contains more than one epitope. So this one reacts with antibody A, and epitope B reacts with antibody B, and epitope C reacts with antibody C. So there are two corresponding definitions of antibodies. So the first one is polyclonal antibody. So what is polyclonal antibody? So polyclonal antibody is a group of antibody that can react with one antigen. Like for this example is antibody A and B plus C adding together is a polyclonal antibody that can react with the antigen, this antigen. And we also have monoclonal antibody. So monoclonal antibody that interacts with only one epitope, which means the antibody A itself is a monoclonal antibody, and antibody B itself is a monoclonal antibody. Okay, so what is antibody? So antibody is a protein that can recognize and bind to a particular antigen with a very high specificity. So this graph show the basic structure of the antibody. So antibody is usually Y-shaped. It has the constant region, so C region, and also the variable region, the V region. So the antigen binding sites are here. So in the V region. So the V region um, uh, is achieved the specificity is achieved by the variable region as a V region. So the antibody is produced by the plasma cells um, in response to the exposure to the certain antigen. Um, Here is another two definitions that we would like to differentiate. One is called affinity and one is called avidity of the antibody. So affinity refers to the strength of a single interaction of the antigen between the antigen and antibody. So as in this graph on the left, so this is an antibody. It's like a IgG in our blood. So it's a monomer. It's by itself. So its interaction, there were two antigen interaction sites. So the strength developed of these two sites is called the affinity. So we have another example here. So this one is a pentamer. So it's like a IgM in our blood. So the strands develop of all these 10 antigen binding sites adding together is called avidity. It refers to the strength of all the interactions combined. So the last concept I want to mention about is the cross reaction. As shown from here, so this is the same antibody, they're identical, and this antibody is able to bind with epitope of a similar structure. So the epitope on the left is structurally very similar to the one on the right. So the antibody is able to bind with both. So this is called the cross reaction. Cross reaction suggests that specificity is never 100%. So theoretically, antibody is able to bind with more than one epitope, most of the antibody. So let's go to the second part, which is the immunoassays. So what is the immunoassay? So immunoassay is biochemical method that can identify and also quantify the unknown analytes. So the analytes of interest, it can be either protein or lipid or nucleic acid, etc. In the body fluid like serum or urine, or even in the solution you prepared. Using the antibody and antigen reaction, there were many different kinds of formats or variations of immunoassays, but the key point is still the antibody and antigen reaction. So that's the basic for the immunoassay, is the antigen bind to the antibody. The immunoassays can be classified into different groups. So this is a very brief classification of the immunoassays. So we classify them into labeled immunoassay, label-free immunoassay, and as also immunoprecipitation. So our focus for today is the labeled immunoassay, which is most widely used, comparing with the other two. And we'll spend the last few minutes to quickly discuss the other two, the immunoprecipitation and the label-free immunoassay. So labeled immunoassays, there were many subtypes. So today we'll focus on these three, which is the radioimmunoassay, enzyme immunoassay, and the fluoroimmunoassay. We'll discuss them one by one. So the labeled immunoassay can be categorized into different groups in different ways. So this one is heterogeneous versus homogeneous assay. So what is the heterogeneous assay? So heterogeneous assay is the immunoassay that requires a separation. So basically, after the antigen and antibody complex is formed, there will be like an isolation and wash step to separate this complex from the leftover mixture. So if there's a separation step in between after the complex formation, and we call them the heterogeneous immunoassay. But homogeneous assay, on the other side, does not require any separation, so we can put them all together to from the beginning to the end. Doesn't need any isolation or washing step. So the label immunoassay can also be grouped as competitive and non-competitive assays. So competitive assay, as we can see from here, this diagram. So this one are the antigens in the serum sample. So basically, these are the analytes of interest. Is something we want to test, and we also created some antigens with labels. So these labels can be different, can be enzyme or fluorescent or isotopes. So we'll put the antigen without label, the analytes, and the antigens with labels together to bind with the antibody. So some antibodies bind with the analytes. Some of the antibodies bind with the antigen with labels. So then we can see from here. So the concentration of the analyte, so the concentration of this group is in basically a negative relation to the intensity of the signal. It's quite easy to understand because if more antibody bind to this group of the analyte, this group of antigen, there'll be less antibody bind to this group, and there'll be less signal generated. So their relation is basically negative. And the competitive assays has two formats. First one is one-step format. Is also called simultaneous assay. So one-step format is we add the antigen without label. So antigen without label is the analyte of interest, and the antigen with label and the antibodies, three of them all together, all in one go, and let them to form different kinds of complex. And this is what we call the simultaneous assay. So there's just one step. And the antibody itself in this reaction is limited. And we could expect most of the antibody is able to bind with either the antigen without label or with label. On the other side, we also have two-step competitive format that we call is a sequential assay. So the first step is the antibody we added is excessive. We added lots of antibody, and the first step will only introduce the analytes, the antigen without label, and let them bind, and there will be some leftover antibodies in the mixture. So after this reaction, after long time, the enough time incubation, and then we goes to the second step. So the second step, we only add the antigen that has label in it to the mixture. So the antigen has label in it will bind to the leftover antibodies to form the complex. So comparing with the one-step competitive format, the sequential assay is more superior than the simultaneous assay. It has higher sensitivity and specificity than the one-step simultaneous assay. Okay, so after I think we've finished talking about the competitive assays. So competitive assay has one step and two step. One step is called the simultaneous assay. Two step is called the sequential assay. And let's get to the non-competitive assay. Non-competitive assay is also called the sandwich assay, that you can hear it very often in the practice. We talk about sandwich assay. So sandwich assay is actually the non-competitive assay. As shown in this graph, so unlike the competitive assay, so the non-competitive assay is we start with coating the surface with a capture antibody. So this is also called a solid phase antibody, which is anchored to a surface, so coated to the surface. And then we add the analytes as no labels on it, only analytes that's of interest to the antibody and form an antigen antibody complex on a surface. And after this step, we add a second antibody. So the second antibody has a label on it. So the labels can either be enzyme or fluorescent or isotopes. We add the second antibody on to this antigen and the antibody complex, and to form this two antibody, one antigen in the middle sandwich structure on a surface. So this is why it's called the sandwich assay. So sandwich assay is a non-competitive assay. So there's no second antigen to compete with the analyte. Instead of have a second antigen, we'll have a second antibody. So the concentration of the analyte is proportional, is a positive relation to the signal intensity. So if it's more analyte in it, there will be more signal generated by the second antibody. So this is a positive relation. from this graph. So in general, the non-competitive assay is superior than the competitive assay, as it has a higher sensitivity and specificity. So sandwich assay is used um, wider than the competitive assay in the clinical practice. There's also some limitations for the non-competitive assay. So there's one listed here that we meet very often in our day-to-day practice, which is called hook effect. So what is a hook effect? As we can see from here, so this is sorry. So this graph is similar to this one, but it has a hook. So why it has a hook here is because so in the working range, as we can see, the concentration and the signal is proportional to each other. Is a positive relation, but when it reached to a certain point, the higher the concentration, the lower the signal. So on the graph, it forms a hook. It's because if the analyzed concentration is too high, so the too is excessive, it's too much. We can see from here. Um, so there will be like more than one antigen will bind to the capture antibody, and when we add the labeled antibody in it, um, instead of the labeled antibody, instead of binding to this antibody antigen complex, it will bind to a free antigen. So the sandwich structures cannot be made in this case. So this is why we can see the signal goes down as the concentrations go up. The hook effect can sometimes cause problems if it's not identified, such as in the HCG assay in the molar pregnancy, because in molar pregnancy the HCG could be like sky high. It may need to the false negative pregnancy test in the molar pregnancy, and especially in some point of care devices. The strategy used for to deal with the hook effect. The first is very straightforward. It's to do the sample dilution. So we bring the sample, the diluted sample, back into the working range in terms of the concentration, and then we're able to perform the assay properly. And the second strategy, alternatively, we can add a wash step before adding the second antibody. So when adding the analyze to the capture antibody, and we incubate it and wash it, and then added the second antibody to it, so the excessive analyte will be washed out, and this to make it a heterogeneous assay to test. Okay, so here goes to the detection system I want to discuss. So as we've mentioned earlier, different labels to the immunoassays can lead to the different detection system. So the most important three are RIA, EIA, and FIA. So RIA is radio immunoassay. So the label is the radioactive isotopes, and we use the radioactive counter to do the measurement. Or EIA is a enzyme immunoassay. So the label is the enzyme, and we use a spectrum photometer to do the measurement. So the EIA, the basic is the change of the color. So you need the spectral photometer to do the measurement. Or FIA. FIA is a fluoroimmunoassay. So it's use a fluorescent as a label, and we need the fluorometer to do the detection. So labels can be applied either to the antibody or the antigen, as we've discussed in the previous slide. If is a competitive assay, like here, yeah. So the label is added to the antigen. If it's a non-competitive assay, like here, the label is added to the antibody. So This slide give a very brief introduction about RIA. Um, RIA can be either competitive format or non-competitive sandwich format. Iodine 125 is the most common isotope we use as a radioactive label. The advantage for the RAA is very sensitive, down to nanogram, and specific as well. And also radio label conjugates is easy to prepare. It obviously has drawbacks. The first is there's risk of radiation exposure, obviously. And also second, the radioisotopes must be used in a few weeks' time. Yeah, so it cannot last for very long once it's prepared. This picture shows typical machine of radio immunoassay. The application of the radio immunoassay is comparatively wide in the lab. Yeah, so it can be used to detect the different pathogens, antigens or antibodies such as hepatitis, HIV, and we use it to detect many hormones and drugs such as HCG, gut hormones. Um, the could use to detect toxins and also tumor markers. So this is an important method that needs to remember. It's a radio immunoassay. So next few slides is about the fluoroimmunoassay. So it's the same picture. The only difference is the label has changed to from the isotope to fluorescent. So the fluoroimmunoassay can be either competitive and non-competitive. And the advantage for the FIA is it's safe. Yeah, it's no radiation. It's safe. It's sensitive and specific, and there's limited background noise, and easy to get the automation. And sometimes you can use different labels are used at the same time. The limitations is um, that rely on the fluorescent detecting system, which is not expensive, not cheap. Yeah, it's expensive, and there's also possibility of photo bleaching. So if you get a photo bleaching, that will, part of the signal will get lost. Yeah. So these are the two examples for the FIA devices. So the application of FIA tends more to be nowadays a point of care devices for some rapid diagnosis, such as the cardiac enzymes, HIV rapid diagnosis, and also during COVID, there's a COVID lateral flow, rapid lateral flow diagnosis. We all use the FIA, and FIA can also be used to test different autoimmune antibodies to help with autoimmune diseases diagnosis. Okay, here comes the most important one is the EIA. So EIA is the enzyme immunoassay. Same picture, changed the label to the enzymes. So EIA can either be competitive or non-competitive. The advantage for the EIA is it's sensitive, safe, quick, cheap, convenient, easy to automation, and is most widely used in the practice. Um, some limitations. First is it needs a monoclonal antibody, and also could be some non-specific absorption. And the enzyme substrate reaction is short term. So once you prepare the EIA, it needs to be read very soon. Otherwise, the signal will get lost. So the most common EIA I believe you all heard about is ELISA. The ELISA is short for the enzyme-linked immunosorbent assay. There were 4 types of ELISA. The type 4 is here. So the first type is called the direct ELISA. indirect ELISA and sandwich ELISA. The type 4 is called the competitive format of these three. So let's begin with the direct ELISA. As shown in the graph here, so for the direct ELISA, the antigen will be attached to the surface, to a surface, and then we add the primary antibody, which is conjugated to an enzyme itself, and it will bind to each other, and this enzyme is able to activate the reaction of the substrate. The substrate change from one color to another. So direct ELISA, as we can see from here, is quite simple. It's short workflow, but it has low sensitivity and specificity. Then they've developed the more superior, which is called the indirect ELISA. So indirect ELISA is similar to this one and the first two steps. So antigen is attached to the floor, and we introduce the primary antibody that can bind with antigen, but the primary antibody itself doesn't have any conjugate. And then we introduce the secondary antibody that's able to bind with the primary antibody, and for secondary antibody is conjugated to the enzyme. And when we add the substrate, the enzyme can do its reaction and to let the substrate to change color. So indirect ELISA is more sensitive and flexible than the direct ELISA. As we know, not all the antigens were able to find a primary antibody that has an enzyme conjugate on it. So for the indirect ELISA, it's much more flexible. Yeah, so we only conjugated the secondary antibody. But there's potential cross reactivity because we introduced the two antibodies into this system. So there's potentially the secondary antibody is able to bind with the antigen as well. Here comes to the third type. So sandwich ELISA. Sandwich ELISA is the best. It has the highest specificity and sensitivity comparing with the direct and indirect ELISA. So sandwich ELISA, as shown here, is like a sandwich assay we talked about earlier. So it has a capture antibody that's attached to the surface, and we introduce the antigen that will bind with the capture antibody, and then is the primary antibody that bind with a different epitope of the same antigen, and then secondary antibody that has conjugated to an enzyme bind to the primary antibody, and then we introduce the substrate to do the detection. So sandwich assay is most widely used ELISA format due to its high specificity and sensitivity. In terms of the enzyme we use, the most common enzymes are HRP, ALP, and AP. For the third group, I do not want to discuss too much further. So third group is what we call the competitive format. Direct ELISA, indirect ELISA, and sandwich ELISA all can be converted to a competitive format, as we discussed earlier, as a competitive assay. So basically introduce another antigen into it. So the competitive format of the ELISA is used to quantify small molecules. Yeah. So here are some pictures to show the ELISA. This is the reading machine. This is the plate we use. ELISA is based on the enzymatic color reaction. As you can see, it's based on the change of the color, and we'll put it into the spectrophotometer to read it. Its application is very wide. We use it to detect the antibodies and antigens associated with pathogens, can be viral, bacterial, fungal, and detector of the tumor markers, autoimmune antibodies we can use as well, different kinds of hormones or drugs, and it can also be used to detect the toxins or food allergens. Yeah, so it's very widely used in the clinical practice. The ELISA. And there's also another EIA uh, that I will only mention very briefly about. So this EIA is called the EMIT. It's called enzyme multiplied immunoassay technique. So sorry, the graph is not very clear, but we can still see what is going on here. So this is a simultaneous competitive assay, which means spontaneous means one step. So that will put everything into the same mixture, all in one go. So what we put in this mixture is the drug we want to test. So this is the analyte of interest, and also a drug that conjugated to an enzyme. So to form this complex. So the drug and the drug conjugate, the substrate and the antibody, the four components adding together to the mixture. So this antibody can either bind with the drug of interest, the analyte we want to test. If it binds to the analyte and the drug enzyme conjugate will not be able to bind with the antibody, so it can bind with the substrate, and in this case, the substrate can give the signal. If the antibody bind to the drug and enzyme conjugate, and the conjugate will not be able to bind with the substrate, and then it will not be able to give the signal. Although it's a competitive assay, but interestingly, the concentration of the drug of this one that we want to test, is in positive relation to the signal generated. So the higher the signal, the higher the concentration of the analyte. So this EMIT is used more often in toxicology, for toxicology screen, or TMD, which is therapeutic drug monitoring. Yeah, it's more used in this area. Okay, so just very briefly about the other two groups of immunoassays. The first one is called the immunoprecipitation. Immunoprecipitation is a very old method that's probably no longer used in our day-to-day practice. The first one is called the radio immunodiffusion. The second one is called the double immunodiffusion. For the radio immunodiffusion, as we can see from here, just very briefly to introduce, um, we have an agarose gel, that's like a disc, and the antibody is everywhere in this disc, and there's a hole in it. In the center, I'll put an antigen here. So the antigen will diffuse across the gel disc, and when the antigen and antibody meet, it will form a precipitation ring. In this way, they trying to estimate such as like IgG subclasses in the past. So it's a very rough estimation. Yeah. Using a radio immunodiffusion. And also similarly, there's a double immunodiffusion. So these agarose plate put the antibody in the middle, and this agarose plate put the antigen in the middle, and they were kind of diffusing in the different in the opposite directions. And when they meet each other, there will be a precipitation line. So this method was first introduced to detect the antibodies for some pathological organisms such as diphtheria or smallpox. And these two are very old methods, probably we do not use it anymore in the day-to-day practice. The last one, unlike the immunoprecipitation, is this is probably our future, is called the label-free immunoassays. So label-free immunoassays, there were many very fancy advanced technology, different kinds of fancy machines. The only one I just very briefly want to mention today is called surface plasmon resonance. So most of the label-free immunoassays, I think it's mainly used in the lab. It's not that much used in our lab practice. So this one is called the surface plasmon resonance. Its key component is still the antibody-antigen reaction. So as we can see from here, it looks like a very complex machine, but actually is they use an optic method to detect the antigen-antibody reaction real time. So there's like a flow channel here. So the antigen will flow through this channel, and there's some antibodies anchoring on this surface. So this surface is made of gold film. There will be a light source here um, to this gold film, and the beam of light to the gold film, and there will be like a refraction to a detection device. Why it's called a plasmon is because of the electrons in the gold film would oscillate when they absorb this light, the energy from the light, and to the oscillation of the electron is called the plasmon. And the plasmon, because of some of the light get absorbed, so there's like some dark field in the refracted beam of light that can be detected. And if there's like antibody antigen reaction here, so the refraction angle will change. So the change of the angle, they can be detected to determine the concentration, the concentration of the antigen. Uh, um, to be honest, I don't know much in details. I'll just pass a message to you. There's also some like fancy stuff, fancy techniques they are developing to use as a label-free immunoassay. So this one is high cost, high sensitivity, and very complex. But it's our future. It's for the future development, especially for some point-of-care devices. Okay, I think yeah, time is up. Okay, I think that's it for today. Yeah, thanks very